Hello everyone and welcome to GTC 2021. Thank you for joining this talk on Conversational AI Demystified. My name is Mariam Bendris. I'm Solution Architect at NVIDIA, based in France. Before we start, I would like to remind you that I am available for chat during the talk, so do not hesitate to submit your questions by clicking on the chat button. Conversational AI applications require a high accuracy and low latency. Indeed, to reach a natural human conversation, the latency needs to be less than 300 milliseconds. In addition, in many domains, reaching a high accuracy is essential. For instance, in healthcare, confusing the name of two drugs having close pronunciation won't be acceptable. However, building such conversational applications is difficult for the following reasons. First of all, multiple modules need to be joined to build the application. For example, this diagram shows the pipeline of a real-time English to Chinese conversation. This application will need to include speech-to-text, natural language understanding for machine translation, and text-to-speech. This is a complex pipeline where errors that can occur in one step are propagated and accumulated, leading to inaccurate results. So in this context, building and experimenting models to get the best performance is challenging. Here is the agenda of this presentation. First of all, we are going through state-of-the-art AI models involved in building conversational AI. Then, we will see how to train and fine-tune such models using NVIDIA NeMo and Transfer Learning Toolkit. And finally, we will discuss deployment challenges for real application and introduce NVIDIA Jarvis platform for conversational AI. Let's start with deep learning models used for building conversational AI. Three main tasks are targeted for conversational AI. The ASR, for automatic speech recognition, takes a human voice as input and converts it into readable text. The natural language understanding, which is considered as the brain of conversational AI, extracts insights from the text. And the third module, the text-to-speech, generates speech from the NLP outputs. So let's focus first on automatic speech recognition. Deep learning has replaced traditional statistical methods such as hidden Markov models and Gaussian mixture models, as it offers higher accuracy when identifying characters and phonemes. In state-of-the-art deep learning pipelines, we first extract features from the audio, such as spectrogram or MEL spectrograms, and train an acoustical model that outputs probabilities for each time step of being one of the characters or phonemes of the vocabulary. Usually, we use a language model decoder for more accurate outputs. Popular deep learning models for ASR includes Wave2Letter, Deep Speech, and more recently QuartzNet by NVIDIA Research. This table shows the performance of several ASR models on the LibreSpeech dataset. For all models, using language model decoder improves the performance of the ASR in terms of word error rate. We can see also that QuartzNet achieves state-of-the-art performance with the advantage of containing only 19 million parameters. So let's see how is the architecture of QuartzNet. This model is divided into an encoder that trains the acoustical feature representation and a decoder that maps those features to the vocabulary. The encoder is composed of multiple blocks containing a 1D time channel separable convolutional layers. This type of convolution allows to reduce drastically the number of parameters, and in conversational AI applications, smaller models offers the advantage of being faster to train and more feasible to deploy when the latency and throughput are important requirements to consider. One can take advantage of the encoder that trains good acoustical feature representation and fine-tune the model on other vocabulary. This is called transfer learning, and it was shown to be effective on different domain-specific vocabulary, English accents, and even different languages. In this paper, authors used QuartzNet model trained on more than 3,000 hours of English audio and fine-tuned the model on German, Spanish, and Russian languages. Results showed that the model benefit from English encoder transfer learning, whether in training convergence speed, shown here on the left, and on the ASR performance, shown here on the right, with the word error rate metrics for the 3 languages. This allows us to take advantage of available annotated datasets in general domain and fine-tune the model on domain-specific datasets. So do consider using transfer learning for ASR when possible. Natural language processing is another task on conversational AI. Going back to our diagram, NLP can be used during the ASR at the decoder step to correct misspelling outputs and for processing the output of ASR text for more complex analysis. So let's first see how to use language model for the ASR output decoder. The output of QuartzNet model is the probability matrix that matches each time step to the vocabulary. To generate the characters or phonemes, the simplest and fastest way is to use the greedy decoder that takes the most probable character at each time step. However, errors and ambiguities can occur on the transcription. This is where a language model comes in. It can help solve those decoding ambiguities. One popular algorithm is the beam search decoder that rescores the ASR output probabilities using a language model. This step may slow down the speech recognition but helps to correct misspelling errors. On the right, we see the evaluation of several QuartzNet models using greedy decoder and a language model-based decoder. And as you can see, language model decoder improves the ASR output. Let's now deep dive into natural language processing. NLP is the task of processing human-level language to extract structured semantic outputs. This is a very hard problem, as natural language is usually unstructured, constantly evolving, and full of ambiguity. There are several tasks involved into conversational AI pipelines, such as machine translation, information retrieval, topic or intent classification, sentiment analysis, and more. Today, state-of-the-art deep learning NLP models are based on transformer layers. This allows to achieve accurate results in many tasks. So let's see what are the main components of modern NLP in the next slides. Modern NLP models are very large neural networks. They are built following 2 steps. First step, called language model pre-training, aims to extract implicit semantic rules of the targeted language. This step is very time-consuming as the model is trained in very large text datasets in a self-supervised way. Indeed, we take advantage of the huge amount of available text corpus and generate synthetic labels to train the model. One example is the masked language model, where we corrupt few words in a sentence and train the model to predict them. Then, to solve domain-specific NLP tasks such as sentiment analysis, in the second step, we copy the pre-trained model, add few layers on top of it, and continue fine-tuning the model on the downstream task with annotated datasets. The third major task involved in conversational AI pipelines is the text-to-speech. Here is the pipeline of text-to-speech application. It takes as input a text, for example, pay $200, and generates the audio. After few pre-processing steps, usually state-of-the-art TTS pipelines generate the audio following 2 steps: an acoustical network that generates spectrogram from the pre-processed text, and a vocoder network that generates audio from the spectrogram. In the next, you will listen to results of TTS pipeline based on Tacotron 2 for the acoustical model and WaveGlow for the vocoder.
You are listening to Tacotron 2 and WaveGlow speech synthesis output.
NVIDIA's solution for conversational AI is based on 3 main pillars. The first one is the NVIDIA GPU Cloud, where we can find several pre-trained models that can be used as starting point for building conversational AI. The second pillar consists in several tools simplifying training and fine-tuning those models and exporting them for efficient deployment. The third pillar is the NVIDIA Jarvis platform, allowing to build efficient pipelines for real-time applications. NVIDIA GPU Cloud, or NGC, hosts several speech, NLP, and vision pre-trained models. Those models are trained over 100,000 of hours and available for free. In addition, there are several monthly updated containers of pre-built deep learning frameworks, such as TensorFlow or PyTorch, optimized for high-performance training and inference. In NGC, you can also find scripts and notebooks documenting how to train and fine-tune those models using NeMo or Transfer Learning Toolkit. Have a look at ngc.nvidia.com to find the list of available materials for conversational AI. Now, let's see how to start building conversational AI models. In the next slides, we will introduce NVIDIA NeMo and Transfer Learning Toolkit, allowing to train models and fine-tune them in custom data. NeMo for Neural Module is an open-source toolkit aiming to simplify building conversational AI with state-of-the-art deep learning-based models. NeMo has several features allowing to hide the complexity of such pipeline. It divides the network into essential components such as the data loader, encoder, decoder, simplifying experimentation for the best architecture. One interesting feature is the neural type, allowing to automatically check semantic compatibility between connected modules. NeMo is built on top of PyTorch and integrates PyTorch Lightning for easy calls to multi-GPU and multi-node training. It is highly optimized for training with NVIDIA GPUs using automatic mixed precision and distributed training. With NeMo, we can train and fine-tune models for ASR, NLU, and text-to-speech. With NeMo, we can have not only pre-trained models, but also scripts for replicating the pre-training and for fine-tuning those models on custom data. In the ASR collection, there are predefined models for Jasper, QuartzNet, and MatchboxNet, and models for speaker recognition and verification. In the NLP collection, there are pre-trained BERT-based and large models for English, name entity recognition model, punctuation and capitalization with BERT, and joint intent slot classification that recognizes intent from a text input and fills automatically the relevant intent fields. In the text-to-speech collection, we can find Tacotron2 and Glow TTS acoustical model, and WaveGlow for the vocoder. On the left, you can see an example of a call for training ASR model with NeMo and PyTorch Lightning. To do so, here we simply specify the number of nodes and GPUs, the backend for data parallel training, and number of epochs. Mixed precision training is enabled by setting the AMP level parameter to a 1 and specify the precision to 16. Mixed precision training offers significant speedup by performing operations in half-precision format. On the right, you can see QuartzNet ASR model performance and training duration going from 122 hours on one node of 8 GPUs to 4 hours on 32 nodes of 16 GPUs. Here is a simple demo showing how to explore ASR models available in NGC. First of all, let's have few audio samples from the test set of the AN4 dataset.
June 18th, 1968.
10/27/62.
Let's import NeMo ASR collection and download the pre-trained English QuartzNet model from NGC. In our case, it was already cached. Let's now query the model with our audio samples and show the results.
June 18th, 1968.
10/27/62.
Using NeMo, you can also fine-tune the English QuartzNet on other datasets for different languages. For French speakers, we fine-tuned the English model on the French subset of the MCV dataset. Let's explore that model. Okay. load an audio sample. Bonjour, vous écoutez le résultat d'un système de reconnaissance de la parole entraîné avec l'outil Nemo. Now query the model and show the outputs. To improve the results, we can use a language model decoder to correct the ASR outputs. We can also continue fine-tuning the model on additional datasets. Another tool used for fine-tuning AI models is the NVIDIA Transfer Learning Toolkit. It offers the easiest and fastest way of building deep learning models with zero coding. It integrates a selection of highly accurate models with the purpose of maximizing deployment performance. Transfer Learning Toolkit can be used for building computer vision models such as body pose estimation, emotion classification, face detection, landmark estimation, and more. TLT offers also the possibility of building conversational AI models for speech recognition and natural language understanding. Here is an example of how to fine-tune ASR model with Transfer Learning Toolkit. After data preparation, create the experiment specification file defining the architecture and the fine-tuning hyperparameters such as the optimizer and the number of epochs. Then, simply run the TLT speech-to-text fine-tune command with the relevant arguments. Let's see this procedure in action. Here is a demo showing how to fine-tune ASR model with NVIDIA Transfer Learning Toolkit. After setting the relevant path, let's see the list of tasks with TLT. We have several tasks from computer vision and for conversational AI, such as ASR, text classification, question answering, and so on. First of all, let's take our NEMO model and explore it with TLT. To do so, we will simply rename our model with the TLT extension. Let's have an audio sample from the AN4 dataset and query the model with the TLT and show the ASR outputs.
October 1st, 1969.
Here we go. Show the results. October 1st, 1969. TLT allows us to fine-tune the model easily in our custom data. So let's do that with the Russian subset of the MCV dataset. We have already prepared the required training and test data files. The files should look like that. We need to specify the audio file location, the duration, and the transcriptions. Now let's fine-tune the model. We need first to prepare the fine-tune configuration file, where we specify the new vocabulary, the Russian characters in our case, and specify some training parameters. Okay? Now let's fine-tune the model. Here we specify that we want to fine-tune from the English QuartzNet using 4 GPUs during 250 epochs. This is going to take a while, so I'm going to show you how to do that and stop the training. We have already fine-tuned the model out of this demo. Here we go. It started fine-tuning. So let's stop that. Once the model fine-tuned, let's query it. First, let's take an audio file from the test set of the MCV dataset.
Если не будет возражений, я буду считать, что Ассамблея согласна с этим предложением.
Here we see the ground truth annotation. Okay. Let's query our model. Here we go, and show the output. Once you are happy with your model, you can export it for deployment either to Onyx or to Jarvis. So let's do that for Jarvis. To do so, we use the TLT speech-to-text export. Here we go. We have our model ready for deployment within Jarvis. To get started with Transfer Learning Toolkit, have a look at the available resources in NGC. You will find a list of available models for fine-tuning and several notebooks such as the one replicating the previous demo. Once we have built our models, let's see how to deploy them efficiently. In the next, we will see tools allowing to optimize the deployment with the goal of reducing the latency and cost and maximizing the throughput. Several tools can be used for efficient model deployment. First of all, trained models can be compressed to reduce latency and memory footprint. NVIDIA TensorRT allows to optimize deep learning models, including model quantization and layer fusion. Next, to serve those models, several features can be used such as dynamic batching and concurrent models. We will present the Triton Inference Server features, allowing efficient model serving. And finally, we will introduce NVIDIA Jarvis, an optimized deployment platform for conversational AI. NVIDIA TensorRT takes a deep network and builds an optimized engine ready for deployment. TensorRT optimization can be applied to any Onyx-supported framework, and it integrates features such as layer quantization, allowing a low-precision representation, and layer fusion. In NLP, for BERT models, TensorRT uses specific optimization for transformer cells. It also includes a specific quantization when using the activation function used in such architecture. In addition, TensorRT offers a flexible way of representing recurrence to fully utilize the resources. This feature is particularly interesting for TTS models using recurrent layers like Tacotron 2. If you are interested in conversational AI model optimization, do check the TensorRT GitHub to find examples of inference using TensorRT for BERT, Jasper, and Tacotron 2. Deploying such models needs to meet the application requirement, such as low latency and high throughput, which is the number of users that can request the application at the same time. It needs also to reduce the cost, and in some cases being flexible for model updates without disrupting the application. Triton Inference Server is an open source project allowing to deploy AI models with the purpose of minimizing the latency, maximizing the throughput, and the GPU usage. With Triton Inference Server, we can deploy several models for all major deep learning frameworks such as TensorFlow, PyTorch, Onyx, and TensorRT. Triton allows to deploy concurrent models, consisting in running multiple copies of a model in order to maximize the GPU usage. It supports also queries in batch and streaming modes, which is an important feature for conversational AI. Triton supports also model ensembling, mutualizing common processes within different models. And finally, it allows dynamic batching, where the user can specify an acceptable waiting window for grouping requests before running the inference. Triton can be used on the cloud, data centers, and on the edge. It offers a Kubernetes integration for scaling and supports GPU and CPU workloads. In addition, it provides key metrics for measuring the level of hardware usage, helping to optimize the application cost. Now, how about complex pipelines with multiple modules that need to be joined to build a real-time conversational AI application? NVIDIA Jarvis platform is a fully accelerated framework for multimodal conversational AI services. Jarvis platform relies on Triton Inference Server and supports deep learning models trained and fine-tuned with NeMo and Transfer Learning Toolkit. Jarvis simplifies application development with only few lines of code. This diagram shows an overview of Jarvis architecture. First, Jarvis exposes ASR, NLP, TTS, and computer vision models as microservices. It supports batched and streaming modes for ASR and TTS, and for NLP, it exposes several services such as intent classification and name entity recognition. For computer vision, it exposes emotion classification service, facial landmarks, body estimation, and more. The computer vision models are fine-tuned with Transfer Learning Toolkit. Jarvis integrates components for managing the flow of the conversation. The dialog manager is responsible for managing context switching for multiple user conversations and for addressing user requests to the fulfillment engine. The dialog manager uses NLP services outputs, such as domain, intent, and entities, and outputs the next action to take or textual answer. Sensor management and multimodal fusion are responsible for synchronizing different sensors and managing timing for launching AI services. Finally, Jarvis exposes multimodal services such as speaker diarization and look to talk. This allows to activate the conversation when the user directs the gaze to the camera. In the next, we will see Jarvis deployment in action. Here is a demo showing how to deploy question answering model available from NGC within Jarvis. This Megatron model was trained on the SQuAD dataset. After downloading the deployable model, first we need to use Jarvis Service Maker to create the Jarvis model intermediate representation. Let's set the relevant paths and create a Gmir file. Here we go. We have our model ready for deployment. Let's copy the model to the model repo of Jarvis. Now, let's deploy this model within Jarvis. 3 steps are required. We need to configure the deployment by modifying the config file, initialize Jarvis, and start the server. For the config file, we need to enable NLP services as we are targeting question answering model deployment, the model deploy key, path for model repo, and set true to use Gmir file. I have already done that. Let's now initialize Jarvis. This step will generate the optimized models that will be requested for the deployment. I have already done that before. If you do that for the first time, this can take few minutes as it builds optimized TensorRT engines. Okay. Let's start Jarvis. Okay. We can see available services by checking Docker logs. Here we go. Now, let's query our model using Jarvis Python API. So this script takes a context and a question, requests the deployed question answering model, and outputs the answer. Okay. For the purpose of this demo, we took an extract from Wikipedia page of Marie Curie. Let's see the context. Now let's ask some questions. Here we go. How many Nobel Prizes Mary won? 5. Where did Mary study? Warsaw's clandestine flying university. How did Mary die? Aplastic anemia from exposure to radiation. To learn more about Jarvis, you can find 5 blogs introducing Jarvis features and tutorials for building real-time applications. You can also find several pre-trained models available in NGC, ready for deployment within Jarvis. Jarvis is open beta, so feel free to apply if you are interested. There are several sample applications ready to run for virtual assistant, chatbot, and contact application, including ASR and name entity recognition. In the next, you will see an example with the contact application.
Well, if you like, I can set you up with an optometrist to get an eye exam.
That'd be great.
Okay, no problem. We'll get you started with that. I see Dr. Lee's office is close to your home. She's really well rated in our network.
To learn more, several GTC sessions will cover conversational AI and NLP. We have also a Deep Learning Institute content on building transformer-based NLP application in Europe time zone. Also, feel free to join the GTC Connect with Experts session to meet our experts. We are also announcing a new DLI content on building conversational AI application. This training will include lectures and labs for building applications at scale.
Thank you very much for joining this session. Feel free to reach out if you are interested in developing conversational AI applications. Stay safe and see you soon.
And thank you, Miriam, for going through this presentation on conversational AI. It's really a great topic, and certainly a some great material in there. For those online, please remember that you can submit questions through the online tools. So if you do have any questions for Miriam you'd like to ask, now's your opportunity. Certainly try to get through all those now, otherwise we have to follow some later. So I see if you've come through now, I'll go ahead and ask Miriam some questions. So first one here is, how do I access Jarvis?
Yes, sure. Thank you very much for this question. So actually, Jarvis is in open beta. So feel free to register in our website, and you will be able to access the application. Yep.
Yeah. Another is a great one. I think especially in Europe, we have so many languages. Is do NEMO and TLT support other languages?
Yeah, so officially NEMO supports English and Chinese, right? However, this tool allows anyone to train and fine-tune ASR, NLP, and TTS models in any languages. And for Transfer Learning Toolkit, also you can fine-tune and train your models for ASR and NLP. So there was a talk during the previous GTC about using NEMO and Jarvis for speech recognition in Arabic, for example. And there is also another talk during this GTC in using NEMO for language modeling in Tunisian dialect. So have a look at those talks if you are interested to learn more. And as I showed in this presentation also, there was an example on how to fine-tune English QuartzNet for Russian language, for example, with TLT. And there are several notebooks that are available in NGC if you want to replicate those experiments.
Great, some great tips there. What are the differences between NEMO and TLT?
Both actually toolkit aim to simplify building deep learning models. TLT is the easiest way of training your models, as it hides all the complexity of coding, for example. TLT offers also computer vision capabilities in addition to conversational AI. NEMO, on the other hand, is targeting more research community for conversational AI. It is more flexible as it is open source and built on top of PyTorch. So it really depends on the user's objective. So if you would like to use custom architecture for research purpose, so use NEMO. If you want to use state-of-the-art, already validated architecture in your custom data, so use Transfer Learning Toolkit.
Okay, and then is where to start for building ASR model in other languages?
Oh, so basically you need your own annotated data set. So you need to prepare audio files and the transcriptions also, and use TLT and NEMO. So we advise to start with the English encoder as a transfer learning toolkit with QuartzNet was shown to be good. So for that. So you can take actually our checkpoint from NGC for QuartzNet that was pre-trained for hours of English audio, and start fine-tuning this model using Transfer Learning Toolkit or NEMO. Yeah.
Okay. And then how is Jarvis different from other virtual assistant toolkits such as Raza?
Oh, sure. Jarvis is actually compatible with Raza. There is an interesting blog showing how to combine Raza and Jarvis capabilities to build a virtual assistant. Jarvis gives the flexibility of fine-tuning easily ASR and NLP models with the Transfer Learning Toolkit.
Yeah. And then can I use Triton directly for conversational AI?
Yeah, sure. Actually, let's say if you have already trained your models with PyTorch and TensorFlow, you can optimize them using TensorRT and deploy them using Triton Inference Server. Sure. However, you will not benefit from the engineering effort provided by Jarvis for an optimized deployment of such pipelines of conversational AI.
Okay, great. Yeah. The other interesting one is, could you specify more about models available in your cloud?
I guess it's NGC, right? So models, the architecture actually of the models are based on research publications, and models are trained either on open source data sets, and in some cases we use also additional internal data set. So in NGC we provide not only the trained model checkpoint, but also several information such as the hyperparameter that we use for training those models, the accuracy also, and we provide scripts for replicating the training also on public data set. In NGC, you can also find optimized deployable models that are compatible with our SDK, for example, for Jarvis.
Great. So I think that's most of the questions we have to answer right now. So if you do have any more questions, still free to submit those online. We might be able to catch a few more in the next 10 minutes. Otherwise, hope you enjoyed this presentation. Certainly, I think it was a really great presentation, Miriam. Thank you for taking the time, and we hope you enjoy the rest of your GTC sessions. Thanks.